Rational function, the reason it goes with polynomial functions is because now it can be written as a quotient of two polynomial functions. So you have to be able to do everything polynomial before you can do anything with rational functions. Like you have to be able to factor. You have to be able to identify the degree of the polynomial. It didn't help any. But, did that do anything? Not really. You guys can see it okay, right? Okay, so P of x and Q of x are just my two polynomial functions, and Q of x cannot be 0 because it's in the denominator, and P of x and Q of x have no common factors. We're going to cross that bridge on when we get to notes on 19, because then there's going to be a hole in your function. But for now, on 18, there's no common factors. You can't cancel anything out. So a rational function is just a polynomial function over another polynomial function. And if we had done 18a first, you'd see like what all the different graphs look like. So I'm going to still have you do 18a on Monday because it's valuable to look at what they, what type of graph are we producing. But I just kind of wanted to get to some of the algebra when you're face to face. So here are 3 examples of rational functions. See how we have a function now in the denominator? So it's important to recognize that you're going to have some domain restrictions because your denominator can never be 0. So what number would be a bad number to plug into this rational function? Like if I plug in 5, I could just evaluate it at 5. What value will give me an undefined denominator? -1. So x cannot be -1. In the second example, I can't tell what my undefined values are, but I know how to factor because I just took a test on factoring. So what will this factor into in my denominator? What are the factors of -6 that I'm looking for? What is it? 2 and 3. Which one needs to be negative? -3, right? So, right, -3 times 2 is -6. Outer plus inner adds up to -1x. Once I have it factored, I'm basically finding the x-intercepts. What makes each of these equal 0? 3 and -2. So x cannot be 3 or -2. See how what you just learned impacts this unit because you need to be able to factor and find the x-intercepts, the zeros. And what's the only undefined value for that third one? What's the bad value? Don't plug this in. What would it be? What's going to make that 0 right there? 1. Don't overthink it. You know how to do this. All right, so we're going to have some domain restrictions in rational functions. So graphing rational functions. Here is the 4 steps that we're going to learn in 18. Here's a quick summary. We'll practice a lot. Basically, you're going to be looking at graphing rational functions for the next 2 weeks. So when you come back, we're going to do like a day or 2 max of review and do our test on rational functions. All right, this is your rational function unit, so don't get behind. 2 major things that you need to find: x and y intercepts and all the asymptotes. And then if we want to find more points on the graph, all we have to do is plug in x values. You can find whatever you want by just plugging in x values. There's 2 major things to remember. These are functions, so they'll always pass the vertical line test. Is this a function? Would that pass the vertical line test for a function? Yes, right? Would this be a function? No, that just failed the vertical line test. So when you look at the exploration and when you start graphing these elbows that make up rational functions, you're never going to graph one on top of the other. So it allows you to figure out where the sections of the graph are going to go. And graphs are always going to hug asymptotes. So if this is my asymptote, this elbow gets closer and closer and closer to the asymptote. So once we know the intercepts and asymptotes, we can graph these rational functions. So the first part here is, to me, the easier 50% of rational functions. There's intercepts and asymptotes. Intercepts should be easier for you. You're just coming off polynomial functions. To find a y-intercept, it says just compute f of 0. I'm going to write down plug in 0 for x. You should already know that. Plug in 0 for x. That's what we did with polynomial functions. So I'm going to go through these 4 examples and just find the y-intercept. Then I'm going to come back to this step. Plug in 0. What would you get here? Plug in 0 for all the x's. And what do you get? What? Yep, 2 over negative 9. So 0, comma, I'm just writing it as the fraction negative 2/9, right? If one of them's negative, positive divided by a negative is still negative. So, all right. What happens when I plug in 0 in the second example, g of x? I get 0 in the numerator. And what do I get in the denominator? And what is 0 divided by negative 9? 0. 0 divided by anything is always 0. So 0, comma 0 is my y-intercept. What would you get on h? So when you plug in 0 for all those x's, what do you get? So 0, comma, negative 5 on top, or sorry, positive 5 on top, negative 8 on the bottom, but the fraction negative 5/8. And what bad thing happens on the last one, j of x? 1 over 0. Can I do that? No, that's undefined. So there is no y-intercept, and that is okay. Some graphs don't have a y-intercept. So there's a big difference between 0 in the numerator and 0 in the denominator. So that's an important rule to know. If you're lucky enough to be on a calculator section of your test, you could type in 0 divided by negative 9 and your calculator would tell you 0, or 1 divided by 0 and your calculator will tell you error. You can't divide by 0. So if you have a calculator, just double check. All right, so that's the y-intercept. I hope that wasn't something that was too new of a process. Finding an x-intercept. Basically, that's like plugging in 0 for y. Plug in 0 for y. That's all you're doing. But this says you're going to set the equation equal to 0 and solve for x. In other words, let your f of x equal 0. In the case of rational functions, we can just set the numerator equal to 0 and solve. So numerator equal to 0 is the shortcut for x-intercepts. I'll show you why on this first example. This is really y equals 2 plus x over x minus 9, right? Whenever I see f of x, that just means y equals. Can I plug in 0 for y? So if I plug in 0 for y, I now have 2 plus x over x minus 9. What would be the first step in this problem to solve for x? I would multiply by x minus 9 on both sides of the equation to get it out of the denominator. Well, isn't 0 times anything 0? So see how you just end up with the numerator equal to 0? That's why it's a shortcut up here. Just set your numerator equal to 0 and solve, because your first step is multiplying the denominator to the other side anyway. What would make that equal 0? Subtract 2. So negative 2 would equal x then. Negative 2 comma 0 is my x-intercept. So the isolated steps are not hard algebra. What makes rational functions a lot more challenging is keeping all the steps straight. Oh, for this one I plug in 0 for x, but in this one I set the numerator equal to 0, And guess what? There's 4 more rules, vertical asymptotes and horizontal asymptotes. So your brain ends up blurring it together. So this is the test that I'll let you have like a note card on so that you could kind of keep all the rules straight. You still won't have a calculator on the first half, but at least you have a note card to keep all those rules straight in your head. All right, I'm going to set this numerator equal to 0. All right, well, hey, x is 0. 0, 0 should make sense, right? If the y-intercept is 0, the x-intercept also has to be 0. That should make sense. What if I set this numerator equal to 0? X squared plus 6x plus 5 equals 0. Can I tell what the value is yet? What do I have to do? Starts with an F. Factor. I have to find the factors of this trinomial. That's why I want you to get faster at factoring. So what are the factors going to be? Uh, 5 and 1, right? X plus 5 times x plus 1 multiplies to 5, adds up to 6. So I have 2 different x-intercepts. What are they? -5 here and -1 here. So -5, 0 and -1, 0. At least you have some examples to look back at for x and y-intercepts. Okay, what happens on the last one? 1 equals 0. Can that ever happen? So what do you think this is an answer? What do you think the answer is? There's also no x-intercept. There's a reason for that, and we'll see what they look like on the graphs. So those are your first 2 rules, x-intercepts and y-intercepts. And I know I'm going through it kind of fast today. I'm not going to, normally if you did this virtually, that's all I would have done today, and I would have made you practice that skill like 10 times. Today I'm in person with you, so I just want to give you another overview of, I think I'm going to go over division virtually. So I just want to show you what it means to have a vertical asymptote. Vertical means vertical line. So on a graph, a vertical asymptote is a dotted line somewhere that is affecting your graph. And think of our steps so far. For our y-intercept, you plug in 0 for all the x's. For the x-intercept, you set your numerator equal to 0. To find the undefined values, your vertical asymptotes, you're going to set the denominator equal to 0. And it says this is also how we find the domain restrictions. So what bad value of x does this first function have? What can x not be for the denominator to be 0? -3. So this has a vertical asymptote at -3, and the domain is written x cannot equal -3. Do you see the difference in how to write an asymptote equation versus a domain restriction? An equal sign versus a slash through? All right, guess what? I need factoring in the next example. Factor that denominator. So what are the factors of +1 that add up to -2? Wouldn't that be -1, -1? What's my only vertical asymptote? 1. And then my domain restriction, the reason it's 1, it's always the opposite of what's in the factor, right? 1 minus 1 is what gives me 0. You guys were mostly starting to get this on that test. All right, so that is your third rule, vertical asymptotes. So you've got y-intercepts, x-intercepts, vertical asymptotes. Here's your last rule, horizontal or slant asymptotes. It says you need to look at the highest power of x, meaning the degree, in the numerator and denominator, and we're going to compare them. Here's your 3-part rule, A, B, and C. That's why you need a note card. It's a lot of rules to memorize. So it says if the largest power is in the denominator, the horizontal asymptote is y equals 0. An asymptote is, what is the graph approaching when x is really big? If x is 1,000,000 and you have 1 divided by 1,000,000, isn't that a really small number? 0.000000001. So that's why the asymptote is y equals 0. If the denominator wins, it's y equals 0. If they're the same, this is a linear function over a linear function. Degree of 1, degree of 1. Or you could do degree of 2 over degree of 2. You strip the coefficients of the two terms. So for this function, the horizontal asymptote is at 2/3. If I plug in 1,000,000, I would have 2,000,005 over 3,000,000 minus 2. 2,000,000 divided by 3,000,000 is 2/3. So it's approaching 2/3. And this is the last one, and this is the reason we need to review division, because I don't know where you guys are at with division of polynomials. You might never have touched it before. So that way, at least sending you off, you've seen how to do this once through, and we can just practice it in the upcoming weeks. If the larger power of x is in the numerator, it's a slant asymptote. I should circle this. So if the denominator wins, it's y equals 0. If they're equal in powers, you peel off the coefficients. If the numerator wins, there's a slant asymptote. We have to do division. So has anyone ever done the box method for division in Algebra 2? Yeah. No? I'm going to show you division. So you have all the skills you need to practice this. And I'm hoping in 2 weeks this is going to get easier and easier, I hope. Here's how you do the box method of division. It's basically factoring or multiplication in reverse. You want to divide this quadratic by this linear function. This linear function is called your divisor. Your divisor goes down one side of the box. Your quotient is going to show up here. So these two things multiplied together are going to give you your dividend. This is called the dividend if you care. This is called the divisor. This is the quotient. Right? Those are the different pieces of a division problem. Okay, if you want your dividend to show up inside this box, the first term that's going to go in the box is x squared. X squared goes here, x squared. What number needs to go up here so that this term times this term gives you x squared? X, right? See how this is very similar to what we've been doing? Now, I can do x times -3, and I get -3x in this box. Now I'm going to look across this diagonal right here. How many x's are in my dividend? There's +2 x's in my dividend. How many x's need to go in this box so that when I add them together, I'll get 2x in my dividend? I'm at -3 in the whole. I need to get up to +2. How much do I have to add? 5 x's. Together, those like terms add up to 2x over here in the dividend. So what's the last term in my quotient up at the top? What times x would give me that 5x term? So x plus 5 is the quotient. I'll just show you how to get the remainder in case you ever have to do this just for the sake of division. 5 times -3 is -15. What remainder has to go here so that these two together add up to the 7 that we wanted? Yep, what number has to go here in this circle so that these two boxes that are diagonal, like terms, have to add up to this +7? Huh? Did you say it? 22. 22 is the remainder. I can't put anything here times x to get just 22. So 22 is called the remainder for this division problem. And y equals x plus 5 is my slant asymptote. Is that new for everyone in here? Division is a new thing that you've never done? I think 2 years ago we did it in advanced algebra 2. But if you took algebra 2 during remote learning or you took CP algebra 2, you've probably never seen division before. All right, let's identify first which of these we'd even have to do division on, and then we're going to practice division a couple more times. Where is the numerator higher? Yeah, the first one, it's higher, right? So let's do division on the first one. It's also higher on the other two, but okay. So when the numerator is higher, we do division. What is a quadratic divided by a linear function? A linear function, right? X squared divided by x is x. What about over here? What is x cubed divided by x? Quadratic. This is not going to have an asymptote because your quotient will be a quadratic. Asymptotes are lines. What would this one be? X cubed divided by x squared. Will that be linear? Okay, so we need to do division on G and P. So, do you want me to do another one and then you try? Actually, P of x is kind of hard too. Let's do those two and then you'll have to do maybe this page as our end of the day, okay? And then we'll end there. I'm backwards. Okay. X plus 4 goes down the side of your box. We'll make you good dividers at least so that this is a skill that you know how to do. I need to put 2x squared inside the top left. This is the quotient that I'm looking for up here. That's going to be my asymptote that the graph approaches. What's the first term of that asymptote have to be? 2x. So I put 2x at the top of the box. Now I multiply to get that bottom missing piece, which is 8x, right? Now I look across the diagonal. I need 3x in my dividend. How many x's have to go here so that these two together add up to 3x? Negative 5 x's. See, together those add up to 3x. All right, now I do outside of the box. What has to go here? So that times x, right, so minus 5, that's my asymptote right there. Let's finish to get the remainder. Negative 5 times 4 is negative 20. What is the remainder for this function? These two together have to add up to what? So positive 19 is the remainder for the division problem. But y equals 2x minus 5. I'm going to show you how to graph that. If you can do the algebra, the graphing is actually the easy part. It's finding the four pieces, the intercepts, the asymptotes, keeping it all straight. That's the hard part. If you can do the algebra, the graphing part actually is easier, believe it or not. Let's do this one together, and then I'm going to have you do the 4 on the front page as your practice, and we'll be on our way to the weekend. So, here we go. I'm going to do a 3 by something box. I might need another box over here. I don't know. I might need one more. I don't know. This is a trinomial as your divisor. So you put 3 boxes down the side, and you're still going to put your first term, x cubed, in that top box. What term goes up here in my quotient? X. So this time you follow down underneath. You have to fill in these 2 boxes this time. So it would be 2x squared and 1x. I'm just going to put a 1 there so that I remember the coefficient is 1, but you could just write x. What goes in this box? These 2 boxes are my x squareds. I need to get negative 2x squared in my dividend. Yeah, negative 4x squared. Are you with Dylan on that one? Yeah, this is challenging algebra. You probably haven't done this before. All right, what goes on the top? Negative 4. You're technically done. You found your asymptote. Y equals x minus 4 is the asymptote. However, if you want to see what the division does, you'd get negative 8x here and negative 4 in the bottom. These 2 terms are going to be both remainder terms this time. Along this diagonal, you have to add up your x's, and along this diagonal, you have to add up your constant term. So if you have 1x and negative 8x, what do you have to add to get to 1x in the dividend? You need to get to positive 1x. You actually already have positive 1x. Don't you just have to negate that with 8x? So 8x is a remainder. And what has to go right here so that these add up to -9? -5. So that's your remainder, 8x minus 5. So to me, doing polynomial division just to do it, why am I learning division? But there's a reason we need division now. We need to find the asymptote of our rational function. So now division's actually quite useful. Maybe you don't think it's useful anyway, but I don't know, does anyone think it's kind of a fun puzzle? I kind of like division. To me, it's kind of like a mathematical puzzle. It's okay if you like it a little bit. All right, you've got 10 minutes. I'd like you to try these 4 division problems, the page right before. So at least, even though you're not a pro yet on rational functions and all the things, at least maybe you'll be a pro about division. And if not, I need to help you with division before you leave. I don't want that algebraic step from algebra 2 to get you all tangled in rational functions. So to me, I don't care if you find the remainders, as long as you find, the only reason the remainder helps is later when there's holes in the graph. If there's no remainder, there actually is a hole. So I like knowing that there is a remainder, but so that should have been how you set up your box, right? Your first step is to put the m on top. M times m is m squared. So step 1, you do the top of the box. Step 2, you do the bottom missing left corner. So once you know that that's -8m, bottom left corner, then you do your diagonal because you know they have to add up to the dividend -7. Yeah, positive 1m plus -8 would be -7, right? So then what goes above that? So plus 1, because 1 times m is 1m. 1 times -8 is -8. What would my remainder be? -3 right here. -3 is my remainder. So if this was an asymptote, they just wanted you to practice the division. So I guess I won't write asymptote, but the answer is m plus 1 with a remainder of -3. M plus 1 with a remainder of -3. Video, I just wanted to have it unpaused to show the answers. And